Hello, very good morning, dear students. Dear friends, today we are going to learn a new concept in chemical bonding, and the title is VSEPR theory. The VSEPR theory is very useful for predicting the shapes of molecules which are covalently bonded to each other. When the atoms comes together, they are forming molecules, and when all these atoms are formed or they are combined by the sharing of electron pairs within them, they are forming covalent molecules. So this VSEPR theory is nothing but it is the short form or acronym for the Valence Shell electron pair repulsion theory. Okay, so what is the long form? Long form of VSEPR theory is Valence Shell. Valence Shell electron pair repulsion theory. So this is the long form of this VSEPR theory. This theory was proposed by the scientists Gillespie and Nielom. Okay, and it was the need at that time to predict the shapes of the molecules and the bond angles between the combining atoms in that molecules. On the basis of VBT, we are unable to predict the correct shapes and bond angles of some molecules. Hence, it is advised or it is needed, there is a need to explain these concepts on the basis of another theory, another concept, and that is nothing but VSEPR theory. So this theory basically is considering the interactions of electron pairs. This theory basically considers the interactions of the electron pairs present in the valence shell of the atoms. In the valence shell of the atoms. So what is meant by valence shell? Valence shell is nothing but, we know that in a multi-electron element or in an atom of a multi-electron element, there are number of shells are possible, 1, 2, 3, 4, etc. And in such cases, the last shell of the electron or the shell in which outermost electron is present or last electron is entering while filling the orbitals or shells, that shell is called as valence shell. And the interaction between these valence shells in that atom are considered while predicting the shapes and the shapes of the molecules and the bond angles between the combining atoms in that covalently bonded molecules. Okay, so this is the central idea of this valence shell electron pair repulsion theory. Let us see the assumptions that are given by this VSEPR theory. These assumptions are also called as postulates. Okay, so what are the assumptions or what they assume to treat these molecules to explain on the basis of VSEPR theory that we are going to see. Okay, so in this multi-atom species or the molecule which are having more than one atoms, the shapes or their electron pairs are considered to be surrounded on the or around the central atom. So central atom is one of the important thing here to express or to predict the shape on the VSEPR theory. Okay, so these electron pairs are surrounded around the central atom in that molecule. Okay, and these electron form pairs. These electrons which are present in the valence shell of that central atom, the electrons which are present in the valence shell, last shell, outermost shell of that central atom, They are surrounding the central atom by forming a pairs. Okay, so electron forms pairs. Okay, electron forms pairs with opposite spin. With opposite spin, and it surrounds the central atom. It surrounds the central atom. So this is the first postulate. Okay, now once the electron pairs are surrounded, there may be more than one electron pairs which are present surrounding the central atom. Now here these electron pairs tend to stay as apart as from each other, or they are tend to stay around that central atom as far away as possible. Okay, so these electron pairs stay apart, means away or far from each other. Okay, so what is the condition here? The electron pairs around the central atom, they are tends to stay away from each other as maximum as possible. Okay, so as to minimize the total energy of the molecule and to increase the stability of the molecule. We know that energy requirement and stability requirement are always inversely proportional to each other. So these molecules are tends to minimize their repulsion, minimize to their energy by keeping the electron pairs as far away as possible. Due to this, repulsions between the electrostatic repulsion between the electron pairs becomes negligible or becomes minimum. Okay, so what is the need? What is the need for these electron pairs to stay away from each other? That the repulsion between these electron pairs around the central atom will be minimum. Okay, so this is the essential condition, that the repulsion between the electron pairs must be minimum. Okay, then the electron pairs in the around the central atom, out of the total electron pairs, some or all electrons may be forming bonds with the peripheral or surrounding atoms. Some or all the electron pairs on the central atom may be forming bonds with the peripheral or surrounding atoms. Okay, so electron pairs forms bonds. Okay, not all, this is not the necessary condition, some or all. Okay, this is the probability. Some or all electron pairs around the central atom may form bonds with the central atom. Now, as we have stated here, not all always, and due to this there are two types of electron pairs. One are called bonded pair of electrons. Okay, in short we call it as a BP, bonded pair of electrons. Okay, so these electron pairs are nothing but the pairs of electron between the central atom and the peripheral atoms which are forming bonds between them. They are called as bonded pair of electron. Okay, and another type of electron pairs are nothing but non-bonded. They are also called as lone pairs or unshared pairs of electron. non-bonded pairs or lone pairs of electron which are not involved in the bonding between the central atom and the peripheral atom. Okay, so they are called as non-bonded or lone pair of electrons. They are designated as LP. Okay, so depending on this, there are two types of electron pairs such as bonding pair and lone pairs of electron. Okay, now it is assumed that, as these are assumptions, it is assumed that the space required for the lone pair in the space required for the lone pair around that central atom will be maximum, will be greater. Okay, so the lone pairs occupy greater space. Lone pairs occupy greater space around the central atom. Okay, so if this is the central atom, then the lone pairs which are present in the orbitals, okay, they are occupying maximum space, greater space as compared to the bonded pairs. Okay, as compared to the bonded pairs of electron. Okay, and hence this is the essential condition that whenever lone pairs of electron are present in the molecule, they must be maximum apart from each other, maximum away from each other. Okay, to avoid the repulsion, electrostatic repulsion between them. Then the next assumption is that the lone pair repulsion, if there are two or more than two lone pairs are present, non-bonded pairs of electron present around the central atom, then the repulsion between them will be maximum, will be treated as maximum as compared to lone pair bond pair and bond pair repulsion. Okay, so in short we can write here the lone pair LP, this repulsion is treated as maximum repulsion as compared to LP BP, lone pair bond pair repulsion, as compared to bond pair repulsion. Okay, so this is the strategy to predict the shape of the molecule. Okay, so LP is greater than LP BP is greater than BP BP, means bond pair repulsion are treated as minimum. And the last assumption of this VSEPR theory is that when the central atom is having all bonded pairs of electron, when the central atom is having all bonded pairs of electron, then the geometry of that molecule will be regular. Okay, so this is the central that molecule will occupy or will get a regular geometry. But if it is having non-bonded or lone pairs of electron, then that molecule will occupy or will get distorted geometry. It will not get the regular geometry, it will get distorted geometry. So the last assumption is related to the regular geometry and distorted geometry. Geometry means shape of the molecule. When it is possible regular geometry, when all the atoms, when all the electron pairs are bonded, when all electron pairs are bonded pairs, then we are expecting the regular geometry, regular shape of the molecule. And if lone pairs of electron are present, then we are expecting the distorted, means the molecule is distorted, the shape of the molecule, geometry of the molecule is distorted from its regular geometry. Okay, so these are the assumptions of this VSEPR theory, that is electron forming a pairs around the central atom with opposite spin, then the electron stay as apart as far as away from each other to minimize the electrostatic repulsion between them. Then the third one is repulsion between electron pairs will be minimum Then electron pairs forms bonds with the central atom. Then two types of electron pairs, then which is having greater space, which is require greater space and which is require lesser space. Then the relative repulsion between the LP and BPs, and last one is the about the geometry. Okay, so these were the assumptions. Now on the basis of these concepts and assumptions of VSEPR theory, let us have some molecule. Today our point of discussion for the molecule to be discussed here is ClF3. So we have to study the bonding structure and bonding of ClF3 molecule, or in the similar way we can also predict in the BRF3 molecule. ClF3, that is trifluoro chlorine trifluoride and here bromine trifluoride. Okay, so both the molecules are having same shape, same bond angle, only negligible difference is there in between the bond angles. Okay, so these can be explained on the basis of VSEPR theory. So let us first of all consider the ClF3 molecule. Okay, in ClF3 molecule the central atom is chlorine. Central atom is chlorine, having atomic number 17. We know that. So what will be the electronic configuration? So ground state electronic configuration of this chlorine atom will be 1s2, 2s2, 2p6, 3s2, 3px, 3py and 3pz. Okay, so as there are 17 electrons, 2 plus 2, 4 plus 6, 10 plus 2, 12. Okay, now 5 electrons are remaining. So we have 3 equivalent energy orbitals. So put 2 electrons in 2px, 2 electrons in 2py and 1 electron in 2pz. Okay, so the valence shell of the chlorine atom, valence shell of the central chlorine atom is having, this is the valence shell, that is the last shell, third shell is the last shell. Okay, and it is having 2, 2, 2, 6 plus 1, 7 electrons. In all total the central chlorine atom is having 7 electrons in its valence shell or the outermost shell. Now this chlorine atom is surrounded by the 3 fluorine atoms. So peripheral atoms are fluorine, peripheral atoms, all are same atoms and these are fluorine. The atomic number of fluorine is 9, all are equivalent atoms. Okay, so ground state electronic configuration of this fluorine is 1s2, 2s2, 2p, 2p5, 2, 2, 4, 2p5. So we have to distribute these two 5p electrons in such a way that 2px, 2px2, 2py2 and 2pz1. 2, 2, 2, 6 plus 2, 8 plus 1, 9. So this is the valence shell of this fluorine atom, and valence shell of this fluorine atom is having again 7 electrons, out of which each fluorine is requiring 1 electron to get complete its octet, and each chlorine atom is also requiring 1 electron for the completion of its octet. Now consider this valence shell of central atom only, don't consider the valence shell of the fluorine. So the central atom is chlorine and valence shell of the chlorine atom is having 7 electrons. Now this ClF3 molecule is formed by the combination of 1 chlorine and 3 fluorine atoms. Okay, so the number of electrons around the central chlorine atom are, these are 7, 2, 2, 2, 1, 7 electrons, and 3 fluorine atoms are supposed to give, or they are sharing 3 valence electrons. 3 valence electrons with the central chlorine atom. Okay, so 7 from the chlorine and 3 from the 3 fluorine atoms, 1 electron each from the 1 fluorine atom. Okay, so 7 plus 3, there are 10 valence electrons are present. Okay, so total number of valence electrons present in the ClF3, total number of valence electrons is equal to 10. So therefore we know that how many pairs will be formed? Total number of electron pairs around the central atom will be 5. Around the central atom will be 5. Out of these 5, 3 are bond pairs. 3 are bond pairs with the 3 fluorine atoms. So each fluorine atom is forming a single covalent bond with each fluorine atom. As there are 3 fluorine atoms, so there will be 3 ClF bond, 3 ClF covalent bonds. So out of these 5 bond electron pairs, the bond pairs is equal to 3 and lone pairs is equal to 2. Bond pair is equal to 3 and lone pair is equal to 2. Okay. So VSEPR theory is predicting the type of molecule on the basis of number of bond pairs and electron pairs, number of bond pairs and lone pairs of electron. Okay, so central atom is treated as A, the peripheral atoms are treated as B, okay, and the peripheral atoms are treated as X or B, whatever it may be. The electron pairs, non-bonded electron pairs or lone pairs of electron are treated as E, and hence this notation will be given, and this notation is called as axe notation. Axe notation. A is treated as central atom. Okay, so how many central atom are there? Only 1. So X is treated as peripheral atoms. How many there are? 3. So AX3 will be there, and how many lone pairs are there? 2. Okay, so bond pairs are 3 and lone pairs are 2. So therefore the axe notation of this ClF3 molecule will be AX3E2. Similar can be applied for BRF3. Central atom is only 1, A, bond pair are 3, X3, and lone pairs are 2, so E2, AX3E2. Such type of questions can be asked in your multiple choice type of questions. So what will be the shape of the molecule of ClF3, BRF3, what is the bond angle, what is the bond length, then how many fluorine atoms are present in axial, equatorial, then what is the axe notation of this ClF3 molecule. Such type of short answer or short question or multiple choice questions can be asked, okay, in any type of examination. Okay, that will be on the multiple choice type. Okay, now this is the axe notation. Now on the basis of that we have to predict the shape of the molecule. As the total number of bond electron pairs are 5, we know that VBT is predicting, or VBT is also predicting the same hybridization. So central atom is undergoing here sp3 hybridization of central atom. Hybridization of central atom will be sp3d, sp3d, 1 plus 3 2 plus 1 plus 3 4 plus 1 5. Okay, so 5 orbitals are involved in this sp3d hybridization, and we know that the shape of the sp3 hybrid orbitals is shape or geometry of the molecule will be trigonal bipyramidal. So this is the expected shape. This is the expected shape or geometry of the ClF3 molecule, that is trigonal bipyramidal. Now there are 3 possibilities that these 3 bond pairs and 2 lone pairs, where they occupy, either in the triangular face, planar triangular face, or in the axial face, okay, towards the axis of the molecule. Okay, now we will see these 3 possibilities. So the first possibility is that when we keep, this is the central chlorine atom, when we keep all the fluorine atoms in a planar triangular phase, all three bonded pairs. Okay, so this is the bond pair 1, 2 and 3. Actually this is not the bonds, these are not the bonds. So this is the what we called, this is one lone pair, this is another lone pair. Okay, so there are two lone pairs. These two lone pairs are occupying the axial positions. Okay, and the three bond pairs are occupying the planar triangular phase. Okay, now the second chance is that two fluorine atoms occupying the equatorial position and one fluorine atom is occupying the axial position. Okay, so another possibility is that 1, 2, 3, 4 and 5, out of which take two fluorine atoms at equatorial, one is at axial position and one lone pair here and another lone pair here. Okay, so again 1, 2, 3, 4, 5 total electron pairs are there, out of which two are two bond pairs and one lone pair is at equatorial, and on axial position one is bond pair, another is lone pair of electron. Okay, and the third possibility is that I am drawing C structure where this is the central chlorine atom, the two fluorine atoms this is the second case, and the third one is equatorial axial. One fluorine atom is at the axial and two at the equatorial. One. Okay, so treat it as two at equatorial. Yes, two at equatorial, one at axial. So here two at axial and one at equatorial, and this is the lone pairs. Okay, so these are the three possibilities. So this is a triangular shape, triangular face. Okay, here the two lone pairs are at equatorial and the two bond pairs are equatorial, two bond pairs are axial and one is at equatorial position. Here the case is different. One bond pair, one lone pair is at equatorial, one is at axial, and two fluorine atoms, that is two bond pairs, are equatorial and one is axial, and here this is the third case. Okay, now here we know that lone pair repulsion is maximum as compared to lone pair bond pair as compared to bond pair. Here if we calculate the total repulsion between these two lone pairs and three bond pairs, the total repulsions will be very high. Okay, so here the maximum repulsion will be experienced by the molecule, and hence it will require maximum energy and less stability. So this possibility of this structure will be ruled out completely. Then the next structure is this one. Okay, in which again one axial lone pair is there, and due to these axial lone pairs there again lone pair bond pair repulsion takes place, and it will be greater than this repulsion. What is the C structure here special? In these structures both the lone pairs are present in a equatorial position, no lone pair is present in the axial position. Okay, so these are the axial positions. Okay, and hence the lone pair bond pair repulsion here is minimum. Okay, so this is the triangular face, let us say, and this is axial bond. One is pointing towards you and one is pointing towards the board. Okay, so due to this all these like this we can say, 1 2 and 3. Okay, 1 2 3, 1 2 3. This is a triangular face, and fifth one is pointing towards you. This is axial, this is also axial. As all the means two lone pairs are present on the equatorial position, so there will be less repulsion between lone pair and bond pair. So that's why the structure is correct, C structure is correct structure, and hence due to this structure is showing that the shape of the molecule, neglecting the presence of lone pairs at equatorial position, the shape of the molecule is T shape. Shape of the molecule is distorted T shape. Okay, F F F. So this is the shape of ClF3 molecule, and it is T shape. T shape, distorted T shape or T shape. Okay, the bond angle is between FCl-F bond is 87, around 87 degrees Celsius. It is not exactly 90 degrees, so that's why we call it as a distorted T shape molecule. Okay, so this is the shape or bonding and structure of the ClF3 molecule that can be explained on the basis of VSEPR theory. The same can be applied for the BRF3 molecule, and hence the shape of the BRF3 molecule is also T shape. Expected geometry, expected shape is trigonal bipyramidal, but due to the presence of two lone pairs at the equatorial position, okay, the predicted shape or the actual shape of the molecule is T shape. Okay, so I think you got the point. Okay, so what type of questions can be asked here? What is the shape? What is the bond angle? What is the axial notation? How many number of lone pairs? How many number of bond pairs present in the ClF3 or BRF3 molecule? Okay, such small questions can be asked in your multiple choice type of questions. Okay, and other details we have already seen here. So thanks for watching this video. Have a nice day.